Welcome, everybody. And I know there are audience around the world, so good afternoon, good morning, good evening, wherever you are. So I'm Zizi, and I'm a faculty from NYU Shanghai. I'm on leave and to take the lead of the Shanghai lab. Now, we're all here today because this exciting new area called graph neural nets, which combines graph computing and deep learning. So let me just tell you a little bit what we find out. What are people working on in terms of research? We take a look at the statistics that collected for the last quarter on the users that are using the two platforms, DGL and PyG. So what you can see that is still very strong, fundamental research into models, in the series that are generically applicable to all the models, about 40%, 30%. And there is a non-trivial effort into system research. That's because GNNs are a very different kind of workloads than the usual deep, dense tensor-based workloads. And then there is about 6% of the applications research. Now this number, this portion is very large if you're comparing with like a few years back. So what does that mean is that graph neural nets are applying to some very interesting downstream tasks. And let's take a look at what they are. Now, bear in mind, these are the statistics for the last quarter or so. So when the year moves on, you will probably see a very different mix. You see the user suspects, right? The life science and NLPs, computer visions, computer graphics, civil engineers, reinforcement learning, healthcare, etc. Right? Now, if we zoom down to the next level, what we see is that there's many interesting applications that we didn't even know of, right? Of course, recommenders, knowledge graphs, finance, those things are we know. But combination of different fields like computer vision, NLP, speech plus computer vision, NLP plus speech, so on and so forth, and material science, neuroscience, physics, etc. So what that means is there's sort of a long tail distribution, and it's really nice to see that graph neural nets are making a very wide impact. Let me just talk about two works from our group. Of course, there are a lot of very interesting, exciting work in the field. We're going to hear from Professor Zheng in a minute. So I'm just going to talk about two examples from our group. First is what we call direct repurposing knowledge graph, where we combine several open domain data sources to generate a heterogeneous graph, which has 6 million edges, 100,000 entities, different types, relations, and so on and so forth, which talk about what kind of genes are responsible for certain diseases and what kind of compound, which is a drug, can treat them, and so on and so forth. So one application of this graph, it actually started during the COVID-19 period when we're thinking about how we can help. So in the case of knowledge graph problem that boils down to a link prediction, basically, if you can find a drug that could have treated the similar diseases, at least around that time, this was yield very promising results. Now people are using this knowledge graph for other researches, such as Alzheimer's diseases. So that's one example of large graph. Let me talk entirely different applications. So we work on a problem that called CycleGT, meaning if we talk about a text or long sequences, if the sentence is not meaningless, it must have encoded some knowledge graph or event graph. Now this problem in NLP community is called NLU for natural language understanding. And the other half of the problem is given a graph, how to generate a text that describes the graph. So it's the encoding part, and that's NLG instead. Now you can see that this forms a cycle. I think this is a fundamental building block when we speak and understand each other. That is, you encode a structure information to what I call a rendering structure, which is a sequence, and you decode the knowledge out of that sequence. Now, one thing that is interesting about this problem, which is converting between two modalities of data, is there is not a single one-to-one mapping. That is to say, the same graph can be described with different sentences, which they all mean the same thing. So the mapping is surjective. So by combining cycle training with a conditional VAE, we were able to show that we could generate diverse sentences with a graph-to-text pipeline, right? So this work has just been accepted in AirStat, and the code is out there. So you're welcome to check it out. So those are just examples. Now, back in early 2018, we started to develop DGL out of universities. That's primarily in NYU and NYU Shanghai. And later on, as we moved to AWS, we started in AWS. Okay, throughout the years, we have made many releases. In the middle of 2020, we realized that the code is getting pretty big and complex, and we did major refactorization on the kernels and address issue of documentations, introduce distributed training, so on and so forth, right? So in a couple of weeks, we are going to release 0.6, which I'm going to talk about at the end of my remark. So DGL is being used worldwide with many different places and with different applications, and we're very happy about that. Now, open source releases are not only releases from our team. There are two more releases. At the end of 2019, we had a release, SageMaker DGL, that had DGL on the SageMaker from AWS. About a year later, we have combined DGL capabilities with Neptune, which is a graph database from AWS, and combine that to offer new services. So that brings me to a more holistic usage of DGL. Of course, we started by addressing the needs of the researchers. And later on, we find that there are some domain scientists who are not necessarily interested in innovate on the model side, but they are very interested to apply graph neural nets to the problem at hand, and they have different kind of requirements. And we had developed what we call DGL domain packages. We have two. So DGL KE embeds knowledge graph. Toward this day, I still believe it is the whole SOTA in terms of performance and scalability, and so on. And the DGL Life Science is a package for bioinformatics, drug discovery. If you are in that field, they use a popular package called DeepChem. DGL Life Science is behind it. Now this is all in open source. Now, as I alluded to earlier, by combining that with the different AWS services, for instance, SageMaker, which manages resources, and graph databases, Neptune, we can deliver direct to the customers. So today, if you go to the DGL homepage, you will see a news like that. So open source projects, to be stable, need to be funded somewhere, somehow. And this is what we do in the case of DGL. Now, this gives you an idea. This diagram gives you an idea of how the graph database and DGL works together. Essentially, you have a graph database, sits here, and some other data. And graph database will offer the usual suspects like graph analytics, visualizations, and so on. Now, you take those graph data set, you train that and infer that with DGL, which, by the way, runs on PyTorch, TensorFlow, and MixNet. And that sits on Amazon SageMaker. Now, that gives you sort of a idea of how all things put together. Bear in mind that this is just a version 1, and there's ways to optimize that. So how are DGL being used in real world? Here, there is a pie chart. What you see that's unsurprisingly, there's two biggest use is recommender systems and fraud detection, knowledge graph, drug discovery, and others. Just like the case of research, that's also a long tail distribution. But if we look deeper into what inside, say, fraud detection segments, there are other subcategories. People use that for finance, understandably, being for retail, and for user-generated contents to filter out bad reviews, identify the fraud abusers, and so on and so forth. Now that brings me to the interesting questions, observation rather. That's a tale of two words. So there are other platforms out there, and DGL is only platform that is being actively used both in research land and in the industry for the real users. And you can definitely see that there are two distributions. Right? In the jargon of machine learning, we can talk about distance between the two distributions. Both of them are long tails. Now, the difference between these two distributions creates tensions and gaps, and also, of course, gradients, and that goes both ways. For instance, if you are a graduate student looking for a job, about to get to a job market, you know where those most active markets are. And of course, from the company perspective, we would look at what the active downstream subfields the researchers are working on and exploit that. So for POI6 releases, there are a couple of things. One is we understand that it's not only for researchers who really need to deal with real users, and DGL or graph neural nets in general is sort of a different model. And we pay emphasis on the documentation, including FAQ, which is really driven by addressing many questions from our real users. And then examples. Right? So there are the examples that we verified, ported. I think last time I checked, about 60. And then there are a lot of Zheng papers in DGL that's with codes. The idea here is to bring all the users on the same place. What I often find is I see an interesting model, say in neuroscience, which has some cool idea that you can borrow to some other domains. So that allows people to exchange ideas, reuse codes, and speed up innovations. Now we continue to optimize for distributed training, improve graph partitioning, heterogeneous graph support, etc. And of course, many improvements on system side. Now that was my last slide. Now you can reach us in many ways. There is a very active discussion forum, and we have a Slack channel. I think this talk is announced on Slack channel first, and Twitter's, emails. WeChat group is 4. That's why I didn't put the code up there. And there is columns and blogs and so on and so forth. Thank you. As I think that's it for me, and I can stay a bit for questions. All right. So if there's no question, I'll stay. It's for the last social networking, and we'll have Zhang to take over.
Thank you.
Let me back to you.
Yeah. Thank you, ZZ. And I'll have Dr. Lassoon from Georgia Tech do the next talk. And Dr. Soon, are you able to share the screen?
Okay.
Great.
You can see the screen now, right?
Yes, we can. Thank you.
All right. Okay. Thank you very much for organizing this event, and I'm very happy to give his talk. So today's talk, I'm going to focus on particular aspects of using graph neural nets. So particularly, we're going to see how graph neural nets are used for solving some of the combinatorial optimization problem. So as ZZ mentioned earlier, it doesn't matter what kind of application domain you're working on now. You will see graphs such as in social networking and knowledge graph database. When you are working with drug discovery, you will have this molecular graph, or even a protein interaction network, or interaction between different type of molecules. If you work on transportation problems, you have this transportation network in the bottom here. And if you work on smart city, you will have this electric network coming from a big city. So for all these type of graph data, essentially you can apply graph neural nets and then formulate lots of node property prediction problem or edge property prediction problem, and you'll be able to use graph neural net for that. So, but what I'm going to focus on today is some of these so-called combinatorial optimization problem over networks. For instance, it might be travel and salesman problem in transportation network. It might be advertisement problem where you want to choose some of the nodes in the social network to advertise in a targeted fashion. So actually, I'm going to use one particular problem as a running example to explain how graph neural net can be used for combinatorial optimization. It's related to this social advertising problem when you want to pick a small number of nodes to advertise such that the information can spread fast. So this problem can be formulated as something called the minimum wireless cover problem, where you try to assign a tag or flag to each one of these nodes in the graph. If that particular tag is going to be 1, that means the node is being selected. Those nodes which are not selected is going to be 0. So what you want to do is to select the smallest number of nodes or assign the smallest number of tag of 1 to the nodes, such that for each one of these edges in the network, at least one end of the edge is being selected. So this optimization problem can be written formally as a form like this. I'm going to use this running example. So in this running example, y is going to be the flag, which can be taken value only by 0 and 1. And then you try to minimize the number of flag ones, or the number of nodes being selected. That's why the summation of these tags. And the constraint is that for each one is edge, E is the edge. For each pair of edge, at least one end of edge, right, is being selected. That means at least one end of this edge, the tag or the flag is going to be 1. So the summation of these two flags for both ends of the edge is going to be larger or equal to 1. So it's such a simple problem, but it's an NP-hard problem. Typically, people design heuristic or approximation algorithm trying to solve this problem. So we're going to actually look at how deep learning approach, especially graph neural net, can be useful for learning some kind of strategy for solving this combinatorial optimization, and how it's going to perform in practice when we have this type of deep learning graph neural net based policy. So the learning is possible because typically such combinatorial optimization problem is not just solved once. It's been solved again and again, maybe in a daily basis or hourly basis. Since think about a social platform where you have each one is node being the user, and each one is edge is going to be a social interaction between the pair of users. And if you look at this social network at different point in time, the number of users which are active on the platform will be different, right? The number of nodes in the platform will be different. Sometimes some nodes just disappear because they didn't log in. And sometimes some of the edge maybe disappear because they become inactive. So there are many graphs there you can think about. Every day or every hour is a different graph where you try to solve this type of combinatorial optimization problem. So you can collect lots of historical graphs, and that becomes your library of graphs. You can actually use this library graph trying to learn some kind of graph neural net based policy, and hopefully this learned graph neural net policy is able to solve a new combinatorial optimization problem very efficiently or with a very good approximation ratio. So there are two actually paradigms for designing a graph neural net based policy. One is based on a sequential kind of policy, like what we did in the reinforcement learning, right? You take action in a sequential fashion. So in this particular case, when you have a sequential policy, the node is going to be selected one by one, and the graph may change after each selection. For instance, in this case, if I have a sequential selection policy, I first select this particular node in the middle, which has high degree. I'm going to advertise on this node first. Then once I select it, I will remove all these edges around this particular node, since those edges connected to this node has been covered, right? And then once you done that, you work with the remaining graph with a few edges. You pick the second node, remove the edge, and you continue working on the graph, which is smaller and smaller, okay? Until you solve the problem. Okay, this is a sequential algorithm. We have a very early paper in 2017 using graph neural net for linear policy for doing sequential selection and using reinforcement in the chain is graph neural net based policy. I'm not going to focus on this type of policy today. Maybe in the end, if I have time, I will talk a little bit about this sequential selection policy. I'm going to focus a second type of selection policy, which is something called the distributed local algorithm. So the selection, in this case, node selection, is performed simultaneously. You have some kind of graph neural net policy, which produce some kind of probability of a particular node being selected or not. And then decisions are made, this graph neural net is going to essentially look at the local structure of the graph and determine these probability of a particular node being selected. And all the nodes are being selected in one shot, okay? For instance, you have graph neural net saying this node should have high probability being selected. This node has high probability being selected. After some threshold cutoff, you select these two nodes, okay? You solve the problem, for instance, okay? I'm going to focus on this type of algorithm. And actually, this type of algorithm is also used very commonly in traditional graph computing. For instance, one thing you might be familiar with is these PageRank algorithm, where you have all these web pages linked to each other, right? And then you try to compute a score R for each one is node in this network, and such that the node with high value of ranking is going to be important nodes, right? So Google actually used this algorithm for ranking web page in the very early stage. So this particular algorithm is going to run, in order to determine this ranking R, is going to run in iterative fashion. It's going to, initialize each node with some kind of random ranking, and then you're going to update the ranking of a particular node J here, for instance, in the center here, by the weighted combination of all these other nodes, which sends in the link to this particular node J. So once the node J has been updated, actually, during the time the node J is updated, all other nodes are being updated in a similar fashion. Once you finish one round of update for all the nodes, you come to the second round, and until it converges. And then you get a kind of ranking score for each one of these nodes. This PageRank algorithm is typically also run in this distributed local fashion, and every node only need to send information to the neighbors, right? And they do it in a distributed synchronous fashion until you arrive at the final answer. So graph neural net, in some sense, is bringing this type of distributed local algorithm into a more complex kind of iterative algorithm, kind of make it even more flexible. Instead of pre-design this particular message passing operator here, the message passing operator is going to be learned. In the next slide, we can see introduction of these graph neural nets. So essentially, suppose I have a graph like this with 6 nodes, right? So initially, what you will do is initialize some kind of embedding vector, a vector representation for each one of this node. And then this initialization can be randomly assigned, or it can be produced by some kind of feature xi attached to each one of this node. You have some neural nets which take the original feature of the node and produce the initial embedding for the node. And then once you have this initial embedding, the embedding of each other's node is going to be updated in an iterative fashion and distributed local fashion. Each one is node, for instance, node I is going to take the message from the neighbors So in this case, the embedding from its neighbors, and then you have small neural nets which performs message aggregation and update and produce update embedding. So each one is node is going to perform this type of neural net work-based message passing and message aggregation and update. Okay, after you finish T rounds of this update, you get some kind of vector representation for each one is node. The more iteration T you run for this graph neural net, the larger the neighborhood this particular embedding is going to take into account. You can think about this embedding vector after T iteration is going to aggregate some kind of information from T hop neighborhoods. Then in order to use this graph neural net produce the embedding to solve combinatorial optimization problem, you use this embedding to define some kind of probability of that particular node being selected as the solution of the combinatorial optimization problem. So this output layer is going to take this embedding and have some neural net with additional parameters producing kind of probability. For instance, the simplest will be some kind of fully connected neural net after this embedding, and with some sigmoid function to push it the value to be between 0 and 1. So you can think about it when I have lots of graphs and I use all this graph to learn the graph neural net operator, right? Then it is essentially equivalent to search over the space of graph algorithms, right? And then different graph algorithms is going to correspond to different parameter in this graph neural net here, okay, for message aggregation and transforming the messages, okay? So then in order to actually make these graph neural nets, expressive, have the ability to, learn new algorithm, expressing existing algorithm, then there's a concern there, okay? How do you actually design these graph neural nets? And then what do you actually put into these particular node features? If you don't do that, these type of distributed local algorithm has some limitations. They won't be able to, represent some of the graph algorithms, okay? So what has been done in the literature is if you run graph neural nets, and then you can actually build quite nice correspondence between graph neural nets and distributed local algorithms, such as something called the Weisfelder-Lemon algorithm for graph isomorphism. But the limitation of graph neural nets, if you just run it like what I described in the last slides on the graph, is you only capture information in T-hop neighborhood. But we know that sometimes when we try to solve some of the combinatorial optimization problem, you have to look at the information which are more globally, okay? So information may be coming from somewhere very far away from the graph. So a T-hop neighborhood may not be, enough to capture those information. And another drawback is if you want to capture more global information, you want to increase the T, but when you increase the T, actually we find it's harder to train the graph neural nets. One reason is first, computationally, you had actually run many iterations to pass the message. The second thing is when you're trying to optimize the parameter in this graph neural net update operator, you need to push gradient very deep into the architecture, and that's also very computationally intensive and make it harder to train. And there's also additional gradient vanishing problem as well in graph neural nets. So essentially, without having some kind of global information, the expressiveness of the graph neural net is limited. Yeah, it cannot express some of these graph neural net. There's even formal proof, like if you just use graph neural net with this kind of local propagation operation, you won't be able to learn some graph algorithms with a certain approximation ratio. Okay. So that motivates, actually, that limitation of graph neural net for learning algorithm motivates our recent kind of research to make graph neural net more expressive. And then also, along the way, we also designed some way to actually explain the decision made by graph neural nets, why graph neural net is picking that particular node, and some explainable graph neural net kind of model. So in a high level, so our framework is like this. Since graph neural net is just running in this distributed local fashion, it doesn't capture information beyond T-hop neighborhood. And what we will do is we will actually augment the original graph with some cheap but global features. So you will see exactly what chip means in the later slides. But in summary, you can think about that. You can actually approximate the original graph with some tree structure. One way to do it, approximate the original graph by some tree structure. And then it can be spanning tree or other type of trees. And then you will actually use some kind of traditional algorithm first to obtain some solution in the tree structure. So hopefully, obtaining the tree approximation of graph and solving these combinatorial optimization over the tree is cheap, linear in the number of nodes in the graph, or sublinear. Okay. And once you have these solution from this simple tree structure, even in our case, we augment it with greedy solution, and you're going to add some additional node feature to the original graph, and then run graph neural nets on top of this augmented graph. And you will find that the graph neural net you design is more expressive and is able to learn some kind of policy which help you better solve the combinatorial optimization problem. And at that point, you want to understand which one of these additional features we augment to the node is going to be the most useful for the decision making, or which part of the graph neighborhood, which edge or node is most important for making the decision that we should select a particular node as part of the solution. Okay, that's where the explainable model comes into the picture. Okay, let's first look at the first aspect. How do we actually design a more expressive GNN, or allows it to search for some graph algorithm which are more expressive? Okay. So the kind of the idea we have is motivated by some of the traditional, graph algorithm design paradigm. So actually, there's an interesting algorithm in the theoretic computer science kind of community for solving linear system, big linear systems. Lx equal to b. X is the, you can think about, it's a value attached to each one of these nodes. L is going to be graph Laplacian, right, corresponding to a graph. So the best known algorithm for solving general linear system is this one, right? Or the n to the power 2.373. But if you have a graph Laplacian, the solution to this particular linear system can be done in near linear time, right? So the idea of these very interesting algorithm is essentially carrying out the solution in a two-stage fashion, and very similar to the kind of augmentation idea we have for these graph neural net. So in the first stage of this traditional algorithm, it's going to find something called a low stretch spanning tree. Essentially, the original graph is the grid, okay? And then the spanning tree are going to correspond to these dark edges, okay? So the spanning tree is going to have some property which is called low stretch. That means that since you have the throwaways on the edges from the original graph in the spanning tree, then when you trying to travel from one node to the other node, the distance is going to be increased, okay? But the low stretch spanning tree has the property that even after you throw some of the edges, the distance is not going to be increased by much. And then the low stretch spanning tree can be attained in near linear time, right? And then what you can do is you solve your linear system using graph Laplacian corresponding to this spanning tree. And once you have the solution, you're going to do some kind of local refinement over the solution, yeah? And the local refinement runs in a locally distributed fashion. So this two-stage approach actually motivates or gives us some inspirations on how to augment the existing graph neural net. Essentially, if you have a complicated graph, right? And then what you can do is you augment you first take a spanning tree approximation to the original graph, and you solve your problem in the spanning tree, and the solution of these in the spanning tree typically it can also be done in linear time, right? Very cheap. And you're going to augment the original graph by the solution of the spanning tree and run these graph neural nets on top of this augmented graph, and hopefully you can learn a more expressive kind of algorithm for it. So here is the sort of schematic picture. You take the original graph, you compute a spanning tree based on the graph, right? And then you use some very cheap algorithm to solve the combinatorial optimization in spanning trees. Typically, that's easy. For instance, dynamic program over trees. And then once you have solved these particular combinatorial optimization, supposedly is weathers cover, then you have some of the node selected according to the spanning tree. And you're going to essentially introduce some of these features, graph features into your original graph. If that particular node is being selected, you have an additional bit of node feature, which is 1. And if that particular edge is being selected into the spanning tree, you have some additional edge features corresponding to the in the original graph, which say have a bit of 1. Okay, for those node not selected and edge not selected, you have additional feature which is 0 corresponding to the node or edges. So you can imagine that if I have one spanning tree, I can produce one set of 0, 1 features, right? And I can actually obtain multiple copies of spanning tree. It can be different type of spanning tree or spanning tree with different initialization. You might get different spanning tree, right? It's not unique. And you can imagine that this different version of spanning tree is going to add a vector. Each one is going to add 1 feature. Then a set of spanning tree is going to add a set of features, a vector of features into each one of these node and edges. Right? So you have already augmented the graph with some global information, because the solution of this combinatorial optimization in the spanning tree has already taken into account global information, right? And once you have this augmented graph structure, right, you are going to run graph neural nets on top of this augmented graph structure. So besides spanning tree, which gives you cheap solution and capture some global information, and you can also use some greedy algorithm to obtain some solution, and that's going to add additional node feature to your graph, and you will use graph neural net trying to learn a more expressive algorithm from that point on. Okay. So this is sort of the idea of augmenting the original graph such that make the graph neural net potentially more expressive and learn better algorithms. Indeed, after this augmentation, and we use graph neural net to learn some algorithm, we find that the learned algorithm is much better. And this graph neural net learned with augmented graph. And what you care about in this case is something called approximation ratio for combinatorial optimization problem. So since it's a minimization problem, so the closer the learned graph neural net, the performance is close to 1, the approximation, the better. So we see this new approach with augmented graph is able to produce policies which has approximation ratio very close to 1 across graph of different ranges. Okay, for other approaches, for instance, CP, MP, and neural net, one hot augmentation, random feature augmentation to the graph. So they all result in graph neural net policy, which is not as good as that kind of framework we see here. Okay. Actually, another thing you might be interested in, how do we actually learn this graph neural net? Especially in the case when the graph is very big, it's not possible to use supervised learning for doing it. Then you have to go for something unsupervised. So for supervised approach for doing it, it's possible in small graphs. Essentially, what you can do is you take a graph and you can run some expensive solver, such as some kind of mixed integer linear programming solver, to obtain a global optimal solution, right? And Y star. So you have then, once you have the Y star, then you have some kind of 0, 1, 0, 1 labels on the graph. You can use the graph neural net trying to predict these labels. Okay, that's the supervised learning approach. And sometimes there's some kind of symmetry in the solution. You have to spend a little bit time to take care of the symmetry. For instance, when you are dealing with something like a max cut problem, so you try to divide a node into 2 groups, right? And those darker nodes is going to be the first group, and the lighter node is going to be the second group. And you can flip the grouping label, yeah, and then switching the darker one to the lighter one to the darker one. You'll be defining the same kind of splitting structure. So you have to take care of this kind of symmetry there. So what you can do is you can actually use graph neural net to produce k sets of probabilities, and you will use the minimum of this probability to define your final outputs and to feed these supervised labels. So this is some small, in some sense, detour or things you need to take care of in a supervised case. But this can only be done in small networks, since you require a global optimal solution, a very good solution being produced with expensive solvers. When it comes to very large graph, recently there's some work coming up allowing graph neural net to be trained in unsupervised learning. So that relies on the optimization kind of formulation for these combinatorial optimization problem, where you have the objective function, right? We show in earlier the example for what is covered. You have the objective function minimize the number of nodes being selected, and you have some constraints. So what you will do is you form something like Lagrangian, where you have the objective function here, and you also have the constraints here. And since now this selection of the node is produced by graph neural net, the graph neural defines a probability whether the node is going to select it or not. So you will get expected value of the objective function, right, based on the probability produced by the graph neural net, and then also the expected or the probability of the constraint being satisfied. Okay, your graph Laplacian contains some probability produced by the graph neural net. So instead of having some expensive solver telling you the answer, you would try to actually learn a graph neural net, minimize this objective function, which combines the objective function, expected objective function value, and then the probability of these constraint being satisfied. Okay, so in that way, you learn some graph neural parameter, it produces the probability of node being selected. Okay, so this one doesn't require you to solve the combinatorial optimization using some existing solver, and can be used to train graph neural for very large scale. Okay, so we can see that is the supervised learning approach. That uses unsupervised learning approach. Both version has been designed on those augmented graph I mentioned in the previous kind of part of the talk. So in both supervised version of that and unsupervised version of that is able to actually do very well, okay, on this minimum waters cover problem, and producing kind of policies which are having very small approximation ratio. Okay, comparing to some of these algorithm which approximation ratio, for instance log n approximation to approximation ratio, the practical performance of the learned algorithm in both supervised mode and unsupervised mode is able to beat some of the very strong heuristic algorithm which are already defined there, or some of them is actually very sophisticated as LPSDP based relaxation method. Okay. This is about the extrapolation ability. So essentially, for different curves, you have this graph neural net trained with a different number of nodes. You want to see how it can generalize to node with a much larger number of nodes. So you can see that there's a graceful degradation of the policy learned using graph neural nets. If you learn with a small number of nodes and try to generalize, and then it degrades and the performance gets worse faster. Okay, if you have trained the graph neural net on a larger graph, for instance, that this purple one, so the performance degrades more gracefully. Okay, if you want to apply it to a larger graph, so this is also something interesting. With this unsupervised learning approach, you can actually learn in much larger graphs. So last, I'd like to mention about how to explain the learned graph neural net algorithm. So as I mentioned earlier, the graph neural net is going to define on this augmented graph, right? You have additional node feature and edge feature augmenting this original graph, and you define a graph neural net to produce the selection probability for a particular node, whether this node should be in the optimal solution or not. So what we want to understand a bit is which one is features dimensions, right? It's going to be most useful for determining the selection probability. Or if we are interested in this particular node here, and what are the graph structures around this particular node? What are the neighborhood? In the neighborhood of this particular node, which other nodes or which other edges is contributing most to the explanation to this selection probability? So essentially, we need to produce some explanations which one of these feature or neighboring node edges is the most important for determining the selection of this particular node. So in order to actually design an explainer, we use another graph neural net to define this, the selection of the nodes in the neighbors. So essentially, in the end, what we want to produce is something like this. So the node I is selected because that particular feature in that particular dimension, yeah, is important, and that particular node in the neighbor is important, and maybe even that particular edge in the neighborhood is important, right? You want to produce a discrete kind of indicator that this particular feature, node or edges, are most important for producing that particular selection probability. So in order to produce this selection indicator, which one is node information is important, we actually need to define a second graph neural net. What we will do is we first extracted out the T-hop neighborhood around that particular node I you want to explain, and together with all the edge feature and node feature. And we're going to define the second graph neural net on top of this neighborhood graph structure. And this second graph neural net is going to, in some sense, produce the probability of, or indicator which one is, node is the most important for explaining this, the decision for selecting that particular pink node in the center. Or, this graph neural is going to produce an explanation for which one is edge is important, or produce an indicator which one is a feature is going to be important. And then we actually use something either like Gumbel softmax approach or differentiate through top K approach to actually further optimize these second graph neural net, which I use for explaining which one these graph structure component are most important. And the optimization is done through some mutual information approach. I'm not going to go into the detail. But once you have this second graph neural net, which can help you explaining what kind of structure element is most important for decision making, you can actually look at some of these problems and learn the policy and trying to see whether it's recovering some existing algorithm or discovering something new. For instance, when we try this graph explainer on the what is cover problem, what we find is that for what is cover problem, the explainer shows that the edges around the particular center node, which are being selected, is the most important for contributing to the selection. So this explainer trying to actually put a lot of emphasis on all these edges around the node. So essentially, it looks like if that node has lots of neighbors, high degree node is going to be selected. It actually the learned algorithm seems to recover the greedy approach for selecting the node. Okay, and then based on these explainment, you can also look at instead of the edges, you can also look at which node are being selected. And since each one is node has its own neighborhood, right? To try to explain which other structure element within the neighborhood that particular center node is most important for decision making. And if you actually overlay all the explanation for each one is node, you'll find that some node in the network are being selected more often as in the explanation set than other nodes. So these nodes, I'm going to color it in this kind of darker color. So it looks like the network has some kind of anchor points out there. And these anchor points are very important for making decision whether a particular node need to be selected as the solution of a combinatorial optimization or not. And this node here may not then itself be in the solution set, but for other nodes which are connected to this particular anchor node here, they are very important to be in the solution set. That's very interesting discovery. Actually, in some of the existing work, people have also used the anchor node, a landmark node in a graph, as some tools to define more kind of expressive graph neural nets. So it seems that using the learned graph neural net policy and also this explainer, we're able to discover this kind of anchor node from this graph structure. So with this graph explainer, we can also look at which feature are more important for making a decision, right? Supposedly, you have augmented your graph neural net, the node feature, by 5 different kind of solution. These 3 in the bottom is going to be these 3 colors is going to correspond to the solution of spanning tree algorithms, and this brown color is going to be solution to the greedy solution. So essentially, each node has a set of features, binary features associated with these 5 different algorithms. And here, if you look at each rows of this kind of bar here, and it's going to correspond to the the explaining set, the most important feature for that particular node to be selected into the solution set. So you can also look at when you have explanation budget. That means that if you want to just pick 2 features to explain the decision making, it's going to be determine which feature is important. It's going to look different when you have a budget 3. You want to select 3 features, trying to explain why the decision is being made. So with the explainer model, you can further zoom down a bit to the selection produced by graph neural net and understand which part of the structure in the graph graph neural net is actually extracting information and determine the final solution. With that, actually, I would like to conclude a little bit. Essentially, what I have shown you is a framework for designing a combinatorial optimization algorithm in graph neural nets, in graphs, okay? So in order to make this algorithm expressed using graph neural net more expressive, so what we will do is we will first augment the original graph with some kind of cheap global solution and obtain from, for instance, a spanning tree of greedy solution. Once we have that, we're going to run graph neural net on the original graph. And with the family graph, we can either do supervised learning or unsupervised learning to learn a graph neural net policy to produce a probability whether the particular node should be in the solution set or not. And once you have learned such a graph neural net-based distributed local algorithm, you can also use our explainer kind of model to determine, for instance, for that particular node to be in the solution set, what are the augmented node feature are important, what are the neighboring node important, and what are the neighboring edges are important. So essentially, with this type of pipeline here, you'll be able to explore a larger kind of space of graph algorithms. And once you learn something with a good approximation ratio, you'll be able to use this explainable model a bit to understand what's important, what kind of features are important for obtaining the better solution, and hopefully that can inspire algorithm designer to better design algorithm in the future. Okay, I think it's probably about the time, right? And maybe I can quickly just go through the sequential, the reinforcement learning part a bit. Now this framework is about distributed local algorithm, right? Every node is going to make decision simultaneously using this policy defined by graph neural net. You can also make sequential decision. At that point, you actually need to use a sequential decision making and reinforcement learning framework to formulate the problem. So again, is this a minimum Wallace cover problem? But we have tried similar kind of policy both in the distributed local algorithm setting and the sequential algorithm setting for other combinatorial optimization, such as challenge salesman problem, max cut, and then minimum dominant set, things like this. So what you can see is this is the formulation for the minimum Wallace cut problem. And when you're trying to actually map this algorithm to the Markov decision process, you can think about the reward for selecting a particular node is or the penalty is 1, or the reward is -1, because you want to select a small number of nodes as possible. Every time you select a particular node, you get the reward of -1. And you can think about the current states of your Markov decision process is the graph, the current graph. And when you compute some score for each one of these nodes, it's like you have some kind of action value function, and then the selection or not of a particular edge is going to be an action. So you want to condition the current graph or state, you determine the value of taking that particular action or selecting the particular node. Once you have this action value function, you can have a greedy policy selecting this I star, okay? So, a particular node, and you remove the node from the graph, you update your graph, you just go back to the next action. Okay, this is the NDP formulation of using greedy algorithm for solving this combinatorial optimization problem. So what's critical in this sequential decision-making process are the action value function, right? And in this case, if you want to use graph neural net to model this process, what you can do is you define this action value function using graph neural nets. So you can think about, in this case, we have lots of training graphs. For each one of these graphs, we can run graph neural nets, right? And obtain the embedding, and it's going to use this embedding to define this action value function. And you can learn this action value function with all these training graphs using, for instance, Q-learning, right? DQN, right? Once you have learned this policy, you can apply it to a new graph and perform greedy selection. So I'm not going to go into the, but end with showing you an example. Hopefully we can play this and see the difference. So this is the algorithm learned by graph neural net. This is the greedy algorithm which picked the the highest degree node each time. Here is the edge greedy solution which pick a pair of node with the highest total degree at the time. So this is a minimum vertex cover problem. And every time the node is being selected, the incident edge are being removed. So the better algorithm is going to clear out the graph the faster, right? So you see these deep learning based graph neural net based algorithms able to actually clear out the graph faster. The reason why this happening is graph neural net is actually selecting. We can look at it again. Initially, when you look at this algorithm learned by graph neural net, it's not the best algorithm. It looks like a node greedy is actually pretty good. It's making the graph less dense and then seems to be cleaning out many edges at the beginning, right? So it's still quite dense here for the graph neural net based algorithm. But near the end of the algorithm, things changes. So the greedy based the algorithm is going to produce lots of islands, right? Small disconnected graph. And the algorithms are forced to select this disconnected kind of component, node in this disconnected component. And in the end, they actually finish the graph slower. But a graph neural net is able to, in some sense, take into account both the degree of the nodes and the connectivity of the overall graph structure, such that even near the end of this algorithm stage, the graph is pretty connected. And you can still pick some node and remove many of the edges in one shot. Yeah, you see the graph is quite connected. The number of components is not that much, and then you're able to finish the problem faster. It has some balance, pick some node which has some balance between the degree of the node and connectivity of the graph. So it's very interesting that you discover this type of algorithm, which may be harder to design by human expert in this case. Okay, so with that, I'd like to end my talk. And any quick questions? Otherwise, I will just log off. Yeah.
Thank you, Dr. Sun. And if you would like to ask a question, you can unmute yourself and ask the question, or you can type it in a window, and we can answer them in the order of which we receive them.
This is Didi here. So that's a great talk. I just have a philosophical question. I think unlike other deep learning models, GNNs should be able to explain itself just by looking at the messages sent, the weights on the edges, and so on and so forth. I've seen works, I think you also included, kind of doing a separate, explainer on the side.
Mm-hmm.
And it's sort of that. Because in the other,
right.
You can look at the gradient, the saliencies, and so on and so forth. Is there any way to combine these two? I mean, a good model should explain itself. That's always been my belief.
Right. So actually, there are two ways to build the explainer. Right. One way is, for instance, I can design into my architecture some attention mechanism. Right. For instance, I can have some like graph attention network. You can actually produce some kind of weights for each of these edges. And then when you're doing the message aggregation, you just do weighty aggregation. And that's part of your original graph neural architecture. Once you finish training graph neural, you just look at those attention weights, which is higher. And then you think that particular edge or node is important. And also you can do something you just mentioned. You can look at the gradient, the magnitude of gradient, right? And to a particular, correspond to particular node or edges and use the magnetic gradient as the explanation. So we are using this approach. In some sense, is a post hoc explanation. So it can explain, in some sense, arbitrary graph neural net architecture. Once you finish training graph neural net architecture, maybe it doesn't have the attention in it, right? And then you have this separate graph neural net, which produces a set of weights telling you when this graph neural net making a decision, which one is edge or node are more important. It's a different way of explaining a graph, but the advantage of this approach is when you have a new graph, even you can actually directly apply this explainer to the new graph to do the explanation. You don't need to rechange or compute the gradient again, right? To rechange, you just need the output probability, and you'll be able to explain the decision of the graph neural nets. So someone actually asked a related question: how is this different related to the GNN by Rex and then Yuri? So it's the objective function for learning the explainer is similar, using something related to information theory, mutual information. The difference between the GN explainer and this explainer here is GN explainer in some sense is just learning a set of plane weights, and you have to do optimization each time to come up with explanation for a new node or new graph. But you can think about our explainer is more generalizable. Once our explainer are learned, it can be directly applied to a new graph. Yeah, you don't need to run optimization anymore. You just run the GNN, it will give you explanation. Okay. Right.
Hi, Professor. Can I ask one question?
Yeah.
Yeah. So my question is there any time complexity analysis about your algorithm and like the global optimal? How do you compare them? Because it seems your algorithm, it depends on the number of spanning tree, the number of layer, height and size. So how do you compare?
Right, that's right. That's a very good question. So that's also one kind of design decision we made when we try to augment the original graph. So we specifically picked those, approximating structures which are cheap to obtain. For instance, if you have a graph to obtain spanning tree, hopefully we need to use some linear time algorithm to do it, right? So you're adding some linear time in some pre-processing to before you run graph neural nets. And you can imagine each one is a cheap approximation. The solution of the original combinatorial optimization on this tree structure should also be cheap, right? Hope for linear time. So you use linear time to obtain this type of augmented feature. And of course, the more feature you augment to the node edges, it will actually increase the parameter of a graph neural nets, right? And then that increase is in some sense not super expensive comparing to the original graph neural nets, right? Typically you just increase maybe 10 different features. Comparing to the embedding dimension, maybe a few hundred, it's very small. So at that point, I would just rely on optimized library such as DGL for graph neural net to carry out the message passing computation on GPU, things like this, right? So the extra kind of cost comes mainly from the pre-processing, right? That's going to be linear time, right? The benefit is once you have augmented your graph with these cheap local features, global features, then you can remain running your, a graph neural net distributed local on just T-hops, but it's able to capture more global information, give you the better final results. Okay.
I see. Great. A second question is this like graph neural network very better than the reinforcement one because of the graph neural network itself, or because of the augmented feature from the spanning tree?
Yeah, so in this particular case, the improvement comes from the augmented feature, right? And then you can imagine you can use any existing graph neural architecture, which is good for this problem. And then what you need to do is to just augment the whatever existing graph neuron a little bit by this initial embedding operation, where you embed this kind of node feature into the embedding space such that you can aggregate it with other messages. Things get a little bit more complex when you have edge features, because the edge features is going to modify the message you pass, right? You can actually, using the edge feature, determine some kind of attention mechanism to determine how much message you want to pass. So here we try to emphasize the benefit comes from this augmented feature. The change to graph neural architecture is relatively smaller, right? And the many graph neural architecture explore using libraries such as DGL. You can actually get a best graph neural architecture for a particular problem.
Yeah, I mean, in other words, can you use the augmented spanning tree feature for the reinforcement learning approach?
Yeah, that's right. Yeah, you can also use that for that. And
I
so
see.
this figure I produced is a little bit earlier work from earlier work. At that time, we didn't use this chip global feature yet. But if you augment your graph with the chip global feature and run this sequential algorithm, it should also improve.
I see. Thank you very much for your answers.
So let me see, there are other questions. I will go from the bottom to the top. With the message passing unsupervised learning, how do we prevent a node from accumulating its own information it sent out to make such an effort? How do we prevent? We didn't do anything specific to prevent it uses its own information. We just still run just standard graph neural on the bottom. The only thing you change is in the objective function level. You change to something which is expected objective function of the optimization, and also some probability of constraint being satisfied or not. On the bottom, we didn't do anything, right? You can just use whatever message passing or the architecture from the library, such as DGL, to perform this unsupervised learning. So there's a question, I wonder if the learn algorithm can be used to generate an example in which the optimal set is maximum, minimum, large, small, generative model producing graph with large, minimum vertex cover. The related algorithm can be used to generate example in which, yeah, I have never thought about this problem. You're asking about something like a generative model for graph with some additional constraints, right? That's an interesting question, and I've never heard about it. Typically, there are all these generative models I've seen out there, especially nowadays for the kind of sequential generative model. You're generating node by node and attaching a node to the existing partial graph. There you have some kind of reinforcement like policy. And how do you enforce these additional constraints? I've never thought about. Maybe some idea from the unsupervised learning part may be helpful for in the generating process. Maybe you have an additional part of your objective function measuring the minimum of the cost or kind of objective. Yeah, it's a very good question. Yeah, so if there's some interesting application, that's actually an interesting problem to work on. The chaining on less than 1K node is a bit of surprising, given the earlier discussion of primary used in fraud, and we often have many more logs per incident available. In a sense, what's going on. So in the combinatorial optimization problem, the reason why we work with some kind of smaller graph is, especially in the supervised learning case, we need to produce some kind of ground truth solution for the graph. That's why people use a small graph as example, right? So now we have actually this unsupervised learning approach for learning graph neural net for solving combinatorial optimization problem, we can go up to much larger graphs. And this is a little bit different from the case when we're trying to use graph neural for fraud detection, where you can get graph with millions of nodes or hundreds of millions of edges or even larger. So in that case, it's typically not solving combinatorial optimization problem, but it's some kind of supervised node classification problem. The label is attained by actually having some node being detected is a fraud node or fraud edges, and then use those signal coming from real life as your supervision. And there you can easily have a graph structure which has millions of nodes, many edges. Okay, I think that's the most questions. Yeah, all the questions for the second part. The rest is for DGL. All right, yeah. If not, then no more question, then I will stop my sharing and hand back the control to Wen-Ying. Yeah.
Yep. Thank you, Dr. Zhang. So what I like to do next is, first of all, I want to thank Dr. Zhang and also Dr. Song Le for presenting today. And we very much appreciate you guys' time. And for those of you who would like to stay for the social, feel free to stick around. We'll be here until 5:45 Pacific time. So what I like to do is to ask a few of the members of DGL team as well as the CuGraph team to essentially unmute and introduce themselves. So I'm going to start calling maybe Mingjie, you could unmute and maybe introduce yourself to the user group first.
Yep. So can you guys see me? All right.
Yeah, we can see you.
Yeah. So, okay. Welcome everyone. So my name is Mingjie. So I work in AWS Shanghai lab. I actually is one of the main author of DGL Deep Graph Library. My major research is machine learning and system. So for example, questions about how to build efficient and flexible systems for machine learning problems or large scale machine learning problems. So my previous experience is in, for example, building a system called MXNet and also other systems like MinPy. And my recent work is basically Deep Graph Library. And I am also interested in a lot of questions like how to use these machine learning, especially like graph neural networks, to solve system problems. For example, Professor Song actually talked about a lot about the optimization problem on a graph, and actually in systems there are a lot of optimization problem on graph, like scheduling and like transactions. These are actually naturally graph. So I'm also interested in that, like how to use machine learning to solve these kind of questions, and especially like large scale, so to produce practical usage. So if you guys have interest in like system problems or like building efficient systems, I'm happy to talk about it. And you can also reach out to me. I'm very happy to connect. Thank you.
Thank you, Mingjie. I really appreciate it. And also, we do have a question for you, actually, in the audience. Is the DGL team in Shanghai still recruiting intern students? So I'll let you answer that.
I see. So we are very active in hiring interns because like we are doing a lot of research, and working with students is the most fun part of the whole job. So yeah, so the answer is definitely a yes. So if you are interested, I will actually send out the email. You type the email in the chat, so you can send your resume to the email, and probably you'll hear some word back from us. Yeah, thank you for your interest.
Great. Yeah, thank you, Mingjie. Anyone else would like to do an intro of themselves from either the CuGraph team or the DGL team?
Sure, I'll introduce myself. Yep. Hi guys. So I'm Joe Eaton. I'm one of the NVIDIA part of this. When Ming and I got together and decided this would be a great thing to add for the community to get the information about GNNs out there and all their applications. It's a really exciting field. I live in Austin, Texas, and there's a lot of great technology here in town. what we're trying to, our group in CuGraph is helping to accelerate some of the primitives that come up in these graph neural networks, and we're looking to try to get them out into the world and doing good things.
Yeah. Also, Joe, you might want to maybe tell a little bit about some of the features that the A100 processors that you guys have put in, such as the sparse matrix support.
Right, that's right. Yeah, we've added some special mode in the tensor cores for sparse matrix support, which comes up a lot in graph networks, which are naturally sparse. Graph neural networks have this natural sparsity pattern. Even most neural networks, after you train them, you can prune them back and get some sparsity. So we have actual hardware capability now to take advantage of that, which gives about a 2x speed up over the dense version of the tensor core. So that's only in the A100 chip. Everything since Volta on has these tensor cores, which really can crank out the flops. So they let one chip get into the 10 to 12 teraflop range per chip. So you can do a lot of math.
Thank you, Joe. And next up, we have Alex Fender and from the CuGraph team, and he's going to make an introduction.
Hey everyone, so I work with Joe. I'm the technical lead for CuGraph. As Joe said, we basically do a lot of accelerated graph analytics algorithm. They are made available through a nice and easy to use API with Python. All my background is in graph. I've been doing accelerated graph analytics at NVIDIA for the past 7 years. So yeah, we try to make it as fast as possible. I heard a lot of algorithm that we have in CuGraph, such as minimum spanning tree, page rank. So if you are looking for solving all those problems, those are things we can already help with. And we're also looking at adding more feature relevant to graph neural, like to GCNs in general, like EgoNet, for example, coming in next release.
That's great. Thank you, Alex, so much. And I'll also open up the floor for anyone who would like to introduce themselves. What we can do is to have everyone maybe type in the chat window and put your name there, and I'll call you as the next person to introduce yourself, and then you can unmute and introduce yourself once I call your name. Don't be shy. It's a user group, and it's really meant for, the group owns this particular event. So Xiaoying next.
Hello. So I'm Xiaoying from NVIDIA. I work with Joe Eaton and Alex Fender in the CuGraph team. I just graduated last year from UC Davis. I mainly worked on the graph neural networks during my PhD. Then after I joined the NVIDIA, I also work on the applications of the graph neural networks on like cybersecurity, the robustness of neural networks. And I also working on how to accelerate the training and the inference in the neural networks, in the graph neural networks. Yeah, I used the DGL library from like 2 years ago. Yeah, it is very useful. Thank you.
Thank you, Xiaoying. Yeah, so next up, Anish.
Good morning, good evening, and good night, everyone. My name is Anish Mohan. I'm an architect at NVIDIA. I actually work very closely with the DGL team, primarily on accelerating DGL on GPUs. We just heard about goodness of A100. We've done a lot of work on the graphs, DGL, and also on the underlying side to ensure we get good performance of GNNs on GPUs. If you have questions or if there are any other applications which you're interested in, I would love to talk about how you're using GNN in your world and how it makes things easier for you.
Great. Thank you, Anish. If you want to put your email in the chat window to everyone, then I'm sure folks would love to reach out to you.
I'll do that.
Yeah, thank you so much. Yeah. Anyone else? Okay, great. So I wanted to talk a little bit. Okay, so I actually just saw another email, saw another message there from Donetto. And are there any internship opportunities in Europe as well? So as far as I know, a lot of those opportunities are listed on AWS's website. So feel free to reach out directly to me, or look on our website. I'll be very happy to refer anyone. And I understand a lot of the one of the reasons that folks join these user groups is that they're interested in opportunities. And for NVIDIA, I can't speak for NVIDIA team, but I'm sure they have internships as well, and there's probably available on their website. Anyone from NVIDIA want to comment on that?
Yeah, I'll take a quick look and post notes there.
Fantastic. Yeah. So with that, I'll let if.
So may I just talk just address this question? So I think the internship program in China in my lab is open to global mentorship. So people from our students in our lab actually can be interning with the mentors elsewhere. That's one option. And that is applicable probably for other sites. So I think there is a site in Turbine, right? And there are researchers there, we collaborate. So that's one option that you can consider. And there are internships in US, certainly. Yeah, back to you.
Thank you, Zizi, for the for this, and I think a lot of students would be very interested in this. I think especially in the Shanghai lab, it would be great to have have a lot of global interns. So the next thing I'd like to do is to introduce Grace. Grace has been done an amazing job to help us organize this event. And we actually do have a survey. So like I said, this event belongs to everybody here. We would love to have you to give us some feedback. So what I did is we actually built a little survey very quickly, and I just put that in the chat window. So if you can fill it out, and especially if you feel like there's some content that you would like to learn or have, we can even, try to invite speakers as a group together. And in addition that, if you have any, suggestions, if you want to help out, please do let us know in the survey. And I will, we'll try to address as much of it as possible. And I will try to make this a very inclusive program. So Grace, anything you would like to add to this?
No, I just want to quickly introduce myself. I also work with Anish team at NVIDIA, and I'm part of the developer relationships. So please feel free to connect with me as well. And I'm very happy to be part of this group.
Great. Thank you, Grace. Really appreciate that, all the collaboration that done. So with that, I'll open up the floor for anyone who wants to unmute themselves and introduce themselves, or just chat on the chat window. But this mostly concludes the main part of this program. Again, I want to thank everybody for attending. And if you want to continue to participate and get updates, we do have our Slack channel for DGL, and it covers essentially the user group. So we'll be posting the slides and other things on there, and we'll also be making the videos available today. So here's the chat window. So there's the link for the Slack channel. So we'll keep you updated, and we'll try to also send you emails. Again, we will. This is an event that's a group that's owned by everyone. So the more participation we have, the better we can have help everyone to work on their research, as well as the problems they're trying to solve at their job or in an industry role. So with that, I'll conclude my part of the main part of the program, and I'll go off video. And if someone wants to chat on the main window, feel free to do so. And we will see everyone next month, and the next event is going to be in February, the last Thursday of each month. So it'll probably be February 25th, I believe. Correct me if I'm wrong. Let me just double check on the calendar side here. Yeah, it is. Yeah, that's right. It is February 25th, and it will send out an invite, and it will be using the Eventbrite to schedule and coordinate the effort. All right. Thank you, everyone, and have a great evening or morning wherever you are.
Thank you, Wenming. Thanks for organizing. Great meeting.
Thank you, Joe. Yeah.
Thank you.